welcome back. In this video, we're going to work through an example of a related rates problem, and we're going to follow some steps. So I want you to grab the handout with the related rates steps, and you're going to follow along with me. I'm going to go through those steps. And when you do your homework, I want you to try to follow the steps and number the steps so you know which step you're completing before you move on to the next step. After you do a lot of these, you won't need to number your steps and you won't need to look at the handout. You'll know what you need to do first. But if you skip any of these steps, you're going to be very confused very quickly. The steps we're going to follow are, first, read and understand the problem. That's easier said than done, right? Read the problem, maybe read it a couple of times so you kind of have an idea of the situation. You may not understand everything about everything that you're asked to do, but at least you can kind of picture what's going on. And then in step 2, you're going to start drawing a picture. Almost every related rates problem has a picture, some geometric object of some sort, or a map, a situation. You have to draw the picture and start figuring out the relationships between all the things that are changing in the situation. And then in step 3, you're going to start assigning variables to the things that are changing in your picture. Now, you might label it X or theta or Y, but really it's a function of time. Everything in your picture that's changing is changing with respect to time. So if it's labeled X, it's really a function X of t, and later we'll differentiate with respect to t implicitly or using the chain rule. So it's really important that when you're labeling things in your drawing, that you're not labeling anything that's changing with a number. In the problem, you'll be given a bunch of numbers, but a lot of those numbers are things you're going to plug in later because quantities are changing, but you're going to find a certain rate at a specific time, and that's at the end of the problem. You'll be plugging in some numbers for those quantities that are changing. But in your drawing, you shouldn't label them with numbers because that means they're constant, and they're not. And I'll explain this again when we do this example. After you've assigned variables to anything that's changing and labeled it all in the drawing, then you're going to write down some rates that are given and rates that you're asked to find, but you're going to write it down as a derivative. You're going to write dx dt equals 65 miles per hour, or you're going to say d theta dt equals something that's given to you. Step 5 is important, but you can't do step 5 until you do step 4. So make sure you've got some derivatives written down in step 4, and then in step 5, it says write an equation that relates the quantities that are changing. So you're going to look at the derivatives you've written in step 4. If you've got a dx dt and a d theta dt in step 4, then in step 5 you need an equation that has an x and a theta in it. And then, and no derivatives are in that equation, just x's and thetas and maybe something else that's changing. And then in step 6 you'll differentiate your equation. And that will give you a relationship between the derivatives, dx dt and d theta dt. And then once you've got the relationship between the derivatives, you'll be able to start plugging things in and solving for the rate that you're looking for. And I'm going to go through these steps one by one in the next example. So here's our example. You're going to have to read it a couple of times to picture what's going on. And I'm going to read it with you. It says a boat is being pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. That's a pretty complicated sentence, so read it again. Okay, so then it says if the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Round your answer to the nearest hundredth. All right, so we can see that they've given us a rate and they're asked for another, we are asked for another rate, but we have to draw a picture of the situation to figure out what's going on here. So we're going to do step 2. Step 2 is draw a picture. So here's the water. I have a boat on the water, and then here's the dock. Now it looks like the boat is really close to the dock, so this is not to scale. There's probably a lot more distance between the boat and the dock, but I didn't have enough room. It says that the boat is being pulled into the dock by a rope attached to the bow of the boat. So the bow of the boat is the front of the boat. So here's the rope, it's red, and here's a pulley. So imagine somebody is standing on that dock and pulling that rope through the pulley. Okay, so the boat is getting closer and closer and closer to the dock. And that rope, that red line that I drew, is getting shorter. Okay, so those aren't constant. Those are changing with respect to time. All right, so it does say that the pulley on the dock is 1 meter higher than the bow of the boat. That's a constant. So remember, the bow of the boat is the front of the boat. So the pulley is 1 meter higher than the front of the boat. If I draw a little line from the front of the boat to the dock, I can label this distance 1. That's 1 meter. The pulley is 1 meter higher than the level of the front of the boat. That's the only constant in my picture. Everything else is changing. The length of the rope and that green dotted line, the distance between the boat and the dock, that's changing. So I can't label those two things with numbers. Let's do step 3. Let's start labeling the quantities that are changing. So I'm going to let x be the distance between the front of the boat and the dock. And that is changing with respect to time. So x represents the distance between the boat and the dock at time t. Okay, it's a function of t. And then, so there's x in my picture. Y is going to be the length of rope at time t. So the length is changing with respect to time. So I'm labeling it y, but y is a function of t. Let's do step 4. So we're given a rate, and let's write our rate, the given rate, as a derivative with respect to time. So the rate that we're given is the rope is being pulled in at a rate of 1 meter per second. So that's the length y is changing, and it's getting smaller, right? So when the boat is far away, y is pretty long, and then as the boat is being pulled in, the length of rope between the boat and the pulley is shrinking. So that derivative is dy dt, and it's negative. It's going to be negative 1 meter per second, okay? The way I've labeled it, y is the distance between the front of the boat and the pulley, and that distance is decreasing, so we know that means its derivative is negative. All right, what rate are we asked to find? We're asked to find the rate at which the boat is approaching the dock. So that's the distance x, the rate at which x is changing. So that means we're finding dx dt at a specific point in time when x is exactly 8 meters. All right, so now that we have our rates, dy dt and dx dt, we want to relate the two quantities that are changing. The x and the y need to be related by an equation. So when we look at the picture, we see, oh, we just have a right triangle. So I just pulled that right triangle out. The height is 1, the base is x, the hypotenuse is y. So I can just write down the Pythagorean theorem, x squared plus 1 squared equals y squared. All right, so I have my relationship between the two quantities that are changing. Now I want to differentiate both sides of that equation in step 6 to get a relationship between their derivatives. So the derivative with respect to time of x squared is 2x times dx dt. The derivative of 1 is 0. The derivative of y squared with respect to time is 2y dy dt. So now we're looking for dx dt when x is equal to 8. So let's solve this equation for dx dt. It's equal to y over x times dy dt. And now we know what to plug in for x and what to plug in for dy dt. So in step 7, we're going to evaluate dx dt when x is equal to 8. So that's going to be y over 8 times negative 1 meter per second. And now we notice, oh, we still have a y in our rate. We got to get rid of that y. So what are we going to do there? Well, we have to go back and go, okay, at the moment when x is equal to 8, go back to that triangle, that right triangle. If x is equal to 8, the height is still 1. That just means that y is the square root of 8 squared plus 1 squared. Using the Pythagorean theorem, at the moment when x is equal to 8, we can get a number for y. So y is just square root of 65. So then dx dt is negative square root of 65 over 8. Now, why is it negative? Well, look at the picture. X is shrinking. The distance between the boat and the dock is decreasing. It's a decreasing function of time. So its derivative is negative. And that means it's the velocity. So if I put it in my calculator, I get negative 1.01 meters per second. But go back to the question and make sure we're answering the question correctly. So if we go back to the question, it says, how fast is the boat approaching the dock when it's 8 meters from the dock? It doesn't ask at what rate is the distance between the boat and the dock changing, because that would be negative. That rate would be negative. It actually wants the speed of the boat. It wants to know how fast is the boat going forward toward the dock. And so that's going to be a positive rate. That's going to be the speed of the boat. So we do want a positive answer. So our final answer is that the boat is approaching the dock at a rate of positive 1.01 meters per second. So when you're working through your homework problems, you should have the handout handy and work through all 7 steps and start out numbering the steps so you can keep track of which steps you've completed and you're doing them in the right order. After you do a bunch of these, you will start to feel like you know what has to come before what, and you won't do things out of order. All right, and I'll see you in another video.